In today's video, we're going to learn about the chain rule. This is IBSL 5.6b, the chain rule for composite functions. For our first example, we're just going to review how to find the derivative of a function using our rules of differentiation. So in this first example, we got f of x is equal to 2x squared plus 3 quantity squared. So the only way we know how to work this out right now is to take 2x squared plus 3 and times it by itself. Using the full method, we can simplify this expression to 4x squared. We multiply the first two terms together. 4x to the fourth, plus 12x squared plus 9. And then we can use our power rule to find the derivative, which would be 4 times 4, which is 16x cubed, plus 2 times 12 is 24 times x, plus, and the derivative of 9 is 0. So that is how we find our derivative. For our next example, we have the same binomial, 2x squared plus 3, but this time it's raised to the 10th power. Now we do not want to work this the same way as we worked the last example. There's no way I'm going to multiply this binomial together 10 times. It just takes too much time. So this is an example of when you want to use the chain rule in order to figure this out. Chain rule simply states, look at the most inside function and rewrite that in terms of u. So substitute in the inside function, in this case 2x squared plus 3, and I'm going to let that be u. So I'd write let u equal 2x squared plus 3. Then rewrite the function in terms of u. So my f of x is now going to be defined as u to the 10th. Then find the derivative of the function in terms of u. So that's just going to be 10u to the 9th using our power rule. Then multiply by the derivative of u with respect to x. So I'm going to go over here to where I said u equal and find the derivative of this expression. Now simplify by combining like terms, so I get 40x times u. Now replace that u in terms of x to the 9th power, and that is my derivative. So that's how you use the chain rule. Now please notice my final answer has to be all in terms of x. So here's the official definition of the chain rule. Derivative of y with respect to x is equal to derivative of y with respect to u times the derivative of u with respect to x. Now, these are some key derivatives that you need to know or be familiar with. These are all given to you on the formula page, so you do not have to memorize these. But we will be using them. The one thing I do want to point out is notice that cosecant of x is abbreviated COSEC. Sometimes on the IB exam, it'll be abbreviated CSC. So make sure you know that those two abbreviations mean the same thing. All right, so let's look at some examples. So again, always start the chain rule by letting u equal the inside function. So I'm going to let u equal 3x squared plus 5x plus 2. And then we're going to need to find the derivative of u with respect to x. So I'm going to go ahead and find the derivative of this function. So that's going to be 6x plus 5. Then I'm going to rewrite my y function in terms of u. Find the derivative of this function in terms of u, and then I'm going to times it by my derivative of u with respect to x. Simplify down, and I get 42x plus 35 times 3x squared plus 5x plus 2 raised to the 6th power. And that will be my derivative. Okay, and b, the inside function is 3x, so we're going to let u equal 3 to the x, and then the derivative of that is going to be 3. So rewrite y in terms of u. Derivative assigned from my table, I know is cosine of u, times by derivative of u, which is 3. So therefore, my derivative of y with respect to x is 3 cosine of 3x. The inside function of an exponential is the exponent, so u is going to be x squared. So derivative of u would be 2x. So therefore, y would be rewritten as e to the u. Now this is one of the derivatives that are not on your formula page that you do need to memorize. So the derivative of e raised to a power is always itself. So derivative of e to the u is e to the u. And then I times that by the derivative of u, which is 2x. So my answer is going to be 2x e to the x squared. The very confusing cases of the chain rule is when you have a trig function raised to power. And the reason for this is that you need to know that I can rewrite this as sine of x cubed. So my inside function is the trig function. So u is equal to sine of x. So from my table, I know the derivative of sine is cosine. So I rewrite this as u cubed. And then the derivative of u cubed is 3u squared times the derivative of u, which is cosine of x. Substituting in what u is equal to, I get 3 cosine of x times sine squared of x. Notice that my final answer, I rewrite the square inside the sine function. In example B, my u is also sine of x, so I've already figured out u and du, so I'm going to rewrite this as u squared. So my derivative would be 2u times cosine of x. Replacing u in terms of x, my derivative final answer would be 2 sine of x times cosine of x. Okay, in an example C here, my inside function is cosine of x. I'm going to let u equal cosine of x. Therefore, du is going to be negative sine of x from our table. So rewrite f of x in terms of u, that's going to be u to the fifth. So the derivative of u to the fifth is 5u to the fourth times negative sine of x. Simplifying down and substituting in my u in terms of x, I get negative 5 sine of x times cosine to the fourth x. In our last example here, we have u is equal to tangent of x. And from my table, I know that the derivative of tangent of x is secant squared x. So rewriting f of x in terms of u, that's u squared. Derivative of u squared is 2u times secant squared x. So my final answer is 2 secant squared x times tangent of x. Some problems you might have to perform the chain rule more than once. So we're going to look at some examples where we have to use the chain rule multiple times in a single problem. So in example A here, notice I have the natural log of the sine of 3x plus 1. So I have two inside functions, the sine and 3x plus 1. So you're going to start by looking at the inside function. So I'm going to let u equal sine of 3x plus 1. For this problem, like our previous examples, so I need to find derivative of u. But I have a problem. I have an inside function, so I need to redefine another variable. So I'm going to let v equal 3x plus 1. So derivative of v is 3. So I'm going to rewrite u as sine of v, and the derivative of sine from my table is cosine. So I got cosine of v times the derivative of v, which is 3. So du is equal to 3 cosine of 3x plus 1. Now, that is just finding the derivative of the inside. Now I need to go back to my original function and say let f of x equal the natural log of natural log of u. Now, the derivative of the natural log of u is one that you need to memorize. It's not on the formula page either. It is 1 over u times by my derivative of u, which I've already figured out to be 3 cosine of 3x plus 1. Rewrite our problem, substituting in our values. I get on the numerator 3 cosine of 3x plus 1. And on the denominator, I have u, which is defined as sine of 3x plus 1. Now you can leave it like this, it's completely legit, or you can recall that cosine divided by sine is cotangent, and also a correct answer would be 3 cotangent of 3x plus 1. For example B, our inside function is sine of x squared plus 1. So I'm going to let u equal sine of x squared plus 1. And then du, well, I have another inside function, so v is going to be x squared plus 1. And so dv would be 2x. And I can rewrite u as sine of v. And the derivative of sine is cosine, so that's cosine of v times 2x. So derivative of u would be 2x cosine of v, which is 2x plus 1. Now I'm going to take my f of x function here, and I'm going to rewrite this in terms of u. So f of x is equal to 3u to the fifth. So the derivative of 3u to the fifth is 15u to the fourth times by my derivative of u, which is 2x cosine of x squared plus 1. So therefore, 30x cosine of 2x plus 1 times sine to the fourth of x squared plus 1 would be my answer to this derivative. For example C, we have e raised to the sine of 3x. So we're going to let u equal sine of 3x. But before I can find the derivative of u, I notice I have another inside function, so I'm going to let v equal 3 to the x, so derivative of v is 3. Using my chain rule, well, I can rewrite u as sine of v. Using that chain rule, the derivative of u would be cosine of v times 3, or another way to write that is 3 cosine of 3x. So now my f of x function in terms of u would be e to the u power. Recall that the derivative of e to the u is e to the u, times my derivative of u, which is 3 cosine of 3x. Rewrite this all in terms of x. We get 3e to the sine of 3x times cosine of 3x. Our last example, example D, f of x is equal to the square root of sine squared x plus sine of 2x. First thing I need to know is recall that u is our inside function, which would be sine of x squared plus sine of 2x. Now to find the derivative of this, the first term I have another inside function, so I'm going to let v equal sine of x. So dv is cosine of x. So I can rewrite u as v squared plus, and then here I have another different inside function, so w is going to be equal to 2x, so dw is 2. And I'll rewrite u as v squared plus sine of w. So the derivative of that is 2v times cosine of x plus cosine of w times 2. So derivative of u is 2 cosine of x times sine of x plus 2 cosine of 2x. Now I'm going to rewrite f of x. Recall that the square root is the same as raising to the 1/2 power. So f of x is equal to u to the 1/2. Derivative of u would be 1/2 u to the negative 1/2 times the derivative of u, which I've already figured out to be 2 cosine of x sine of x plus 2 cosine of 2x. Simplifying this and getting rid of our negative exponent and replacing u with our terms of x, my final answer would be the derivative is equal, well, I could rewrite this as derivative is equal to 2 cosine of x sine of x plus 2 cosine of 2x. Divided by 2, the square root of u, which recall is sine squared x plus sine of 2x. 2 divided by 2 simplifies down, so my final answer for this derivative would be cosine x sine x plus cosine of 2x. Because remember, I factored out the 2 before I can cancel it out. I just can't cancel out those 2 front 2's. Divided by the square root of sine squared x plus cosine of 2x. This is an example where it's okay to leave a square root in the denominator. IB doesn't expect you to go any farther than this. This is a good answer. We know how to find the derivative using the chain rule. Let's look at some IB style type questions. So in this example, we're given f of x is defined by the cosecant squared of x, and you're asked to A, find the derivative of f of x, and then B, solve the equation the derivative of f of x is equal to 2 f of x within the domain of negative pi to pi. So let's start with part A. So f of x is defined by cosecant of x quantity squared. So I have an inside function, so I'm going to let u equal cosecant of x. So du, according to my table, is negative cosecant of x times cotangent of x. So I can rewrite f of x as u squared. Derivative of f of x is 2u times the derivative of u, which is negative cosecant x cotangent x, which the derivative therefore can be written as negative 2 cosecant of x squared times cotangent x, because u is cosecant of x. Now that I know what the derivative of f is, I'm going to look at b. So I'm going to take the derivative of f, which we just figured out in part A, to be negative 2 cosecant squared x cotangent x, and equal that 2 times f of x, which is defined as cosecant squared of x. and I need to solve this equation. So in order to solve an equation, notice that I need to get it equal to 0. So I'm going to start by moving this term on the right over to the left-hand side of the equation by subtracting 2 cosecant squared x from each side. Now I notice I have a GCF of negative 2 cosecant squared of x. I want to factor that out for my terms. Now, using my zero product rule, I'm going to set each of these terms equal to 0. And I'm going to solve each of these individual equations, and I'm going to find all answers between negative pi and pi that work in this situation. So I end up with cosecant of x is equal to 0. Now you can solve this any way that you want to. You can use your unit circle, you can use your knowledge of angles. I'm going to use graphical because I'm a very visual person. So I know the cosecant of graph looks like this. And I notice that cosecant is never equal to 0, so there's no solution to this problem. Now cotangent x, I need to figure out when it's equal to negative 1. So I'm going to do a quick sketch of cotangent of x. And I'm going to do this graph from negative pi to pi. So remember, on cotangent x, I have asymptotes at negative pi, 0, and pi. And then I have a graph that goes at halfway point for each of these. So at pi over 4 and 3 pi over 4, I'm at 1 or negative 1. So I have this graph looks like this. So every time I'm at negative 1 is when x is equal to negative pi over 4, or when x is equal to 3 pi over 4. So my two solutions is negative pi over 4 and 3 pi over 4. If you're a little confused about this last part, we had to find the values of the trig functions graphs, you might want to refer to that optional video trig function graph that I've uploaded on Edpuzzle for additional resources and help. Because this is a content that IB is assumed as prerequisite knowledge for this course.